let's start with carboxylic acids and talking about how they react, okay? How they can enter into this matrix of carboxylic acid derivatives. They are typically pretty difficult to react because, first of all, OH is a poor leaving group, right? OH minus is. Hydroxide is a very strong base that can typically just add right back in and reverse the reaction. So the carbonyl is not particularly activated. It's a lot like an ester in that fact that the O of the OH donates electron density in. So reactions at the carbonyl must first involve enhancing the electrophilicity or enhancing the leaving group. Okay? We can activate the carbonyl for attack, or we can make the OH into a better leaving group. Either one of those things are tools that can be used to make a carboxylic acid react at the carbonyl. So let's talk about that reaction I mentioned where we can get our carboxylic acid into that high energy acid chloride, which then can be taken on to react with any of the other reagents. For that, we use thionyl chloride, and that was a reagent that we had seen before by just for converting an alcohol into an alkyl chloride, right? We used SOCl2 for that. So the reaction here of a carboxylic acid, right, to an acid chloride involving thionyl chloride is the same sort of thing. The OH turns into a Cl, so it's an easy way for you to think of it in those terms, easy way to remember it as long as you remembered the reaction of the alcohols before. The mechanism is a little more complicated, and I'm not going to have you recreate this mechanism, but what is important is that you identify what's happening. You know, not necessarily remembering every single little arrow here, but being able to identify what the purpose is of each of these steps. So, first of all, take a look at what happens here. Oxygen donates its electrons in, and that causes the carbonyl oxygen to go and attack the sulfur of thionyl chloride, right? Just like a acyl addition reaction, right? So it forms this tetrahedral intermediate, okay? Just like that, and a lot like the reactions that we've seen before, the O- in that tetrahedral intermediate comes down and kicks off a chlorine, while simultaneously, or I suppose is a different step either way, you can imagine the chlorine that's forming will pick off that hydrogen that was originally the OH of the carboxylic acid. The key here is that the neutral product we get has this OS double bond OCl. And what we've done is formed a good leaving group. So this reaction of the carboxylic acid turned one of those oxygens into a good leaving group. Okay? It's actually the carbonyl oxygen that becomes part of the leaving group. Okay? This intermediate has C double bond O, where the single bond O originally was, so they sort of swapped that way. What happens now is just like an acyl substitution. A nucleophile adds in to the carbonyl. We get a tetrahedral intermediate. The O- comes back down, and it kicks off the leaving group. Okay? This leaving group's a little special because it makes SO2, and then it kicks off chloride from there. We can identify the key components here. Here's a nucleophile adding, a good leaving group that gets kicked out. So that's how we make our acid chloride. So be able to identify the part where we've formed a good leaving group, identify where the nucleophile has attacked. So that's a useful reaction. We'll talk all about acid chlorides, acid halides coming up. So let's talk about anhydrides. It is possible to make an anhydride directly from carboxylic acid because anhydride literally means without water. So if I want to make acetic anhydride, CH3, C double bond O, O, C double bond O, CH3, I can do so by taking just acetic acid, heating it to very high temperatures, and driving off water. So the reason this happens, let's take a close look at the structure. If I have an anhydride, it has this oxygen in between the two carbonyls, right? They share that oxygen. So we essentially had to remove an OH from one of the acids and an H from the other one. Okay, that gives us an anhydride. This only is practical for very simple anhydrides. Anything more complicated than that will probably decompose at the 800 C. So this is really only practical for industrial production of something like acetic anhydride. We'll have a much better way to make anhydrides in a moment from acid chlorides. There are some limited circumstances where we can make esters directly from carboxylic acids. In one case, we have a carboxylate ion, right? So C double bond O minus that can attack a primary alkyl halide by an SN2 reaction. So the O minus just simply attacks the carbon, displaces the I as a leaving group, okay, just from a simple SN2 reaction. A carboxylate is a fairly good nucleophile, and as long as our alkyl halide is primary, we should have no problem displacing it to make ester. So that allows us to make esters with an alkyl group here as long as there's no other substitution on that first carbon. If our alcohol part of an ester over here, the OR group, can come from a simple cheap liquid alcohol like ethanol or methanol or isopropanol, something like that, we can do an acid-catalyzed Fischer esterification reaction. Here's a carboxylic acid. We've added methanol to it along with HCl, right? And it's an acid catalyst. See the mechanism here in a moment. And just like we would expect, the OH is replaced with the OR group from the alcohol. And this can happen in fairly good yields as long as we have a large excess of the alcohol. The Fischer esterification is actually equilibrium driven, so we need to have a huge excess of one of the reactants. It also helps if we can remove or distill away water. So there's special apparatus that can be used to capture water produced in this reaction, and that pulls the reaction along in the forward direction. Pretty much every organic chemistry student in the world does a Fischer esterification reaction in their first semester. What we did was take acetic acid, and we can start abbreviating that ACOH now that we know the acetyl group. Acetic acid and isopentyl alcohol. So 1, 2, 3, 4 with just a branch on the end. Isopentyl. If we have isopentyl or isohexyl or something like that, it just has one branch right near the end of it. And what we did, we reacted that with H2SO4 as a catalyst. We added consulfuric acid to that. We ended up with isopentyl acetate. So the acetyl group, right, comes in from over there. It's actually the O of the alcohol that makes the new O of the ester. We'll see that in the mechanism here, right? So this is isopentyl acetate and water, right? Notice where the water came from, right? The OH of the acid, the H of the alcohol. If we had a isotopically labeled oxygen, we would be able to confirm that it's the oxygen of the alcohol that becomes the oxygen in the product, right? The OH of the carboxylic acid in the first place is removed to make water. So let's just signify that like that. The mechanism of the Fischer esterification should be fairly familiar to us. It's an acid-catalyzed reaction. So once again, we have yet to experience an exception to our rule. If it's an acid-catalyzed carbonyl reaction, we protonate the carbonyl first. That activates the carbonyl for a nucleophilic addition to it, right? C+. So the alcohol adds to the carbonyl, brings the electrons up, okay? Makes alcohol up there. What happens next is a proton transfer. Let's look very carefully at where the proton transfer occurred, okay? What we would do first probably is deprotonate this O plus here on where the alcohol was, and solvent or alcohol molecule, something nearby, can do that. And then we protonate one of the OH groups on the alcohol. So There's our proton transfer. Let's write that here, H plus transfer. Right? That allows us to do an elimination. So water will grab the other H from the OH. That will come down, make a carbonyl. That will kick off the good leaving group. So that gives us our ester, and we've regenerated hydronium for it to protonate the carbonyl of the next reactant. So let's review this mechanism here. This is a very important mechanism that you'll be responsible for. We, of course, protonate first. Our nucleophile attacks. Okay, we should be able to get to this point without much thinking about it. We do a proton transfer now to make water a good leaving group. So we remove an H. Okay, we remove an H from the unprotonated OH. That comes down, making a carbonyl. Right, we reform the carbonyl that we started with originally that expels water as a leaving group. So we have replaced our OH in the original starting material. Take a look up here with the OR from the alcohol. Like we said, it's equilibrium driven. Large excess of liquid alcohol is required, and you essentially reflux them together. If we were to have an excess of water, that would be the reverse reaction. So we'll talk about that with esters. Esters can be hydrolyzed with water back to carboxylic acids with a little bit of acid catalyst. We can make carboxylic acids directly into amides. This is really most useful in laboratory protein synthesis. So when a sequence of amino acids is required to be synthesized together to make a protein, right? Here's an amino acid, right? It's a carboxylic acid with an amine, right? With an N attached to the alpha carbon. Amino acids join together to make amides. Okay? If I have two amino acids, the resulting amide is called a dipeptide, and this over and over again makes a polypeptide and eventually makes a protein. So it's formation of an amide, right, between a carboxylic acid and an amine that way. DCC, dicyclohexane carbodiimide, is used as a reagent that activates the carbonyl, okay, and makes for a good leaving group. So remember I said carboxylic acids, you need to activate the carbonyl, you need to make a good leaving group. In our Fischer esterification, the protonation serve that purpose. Here, we don't do this under acid catalyst. That would protonate the amine here, making it no longer a nucleophile. So we need neutral conditions, and DCC allows for that. So first thing it does, it's actually kind of interesting, DCC, dicyclohexyl, right, those are the cyclohexyl, carbodiimide. So N double bond C double bond N is a carbodiimide. These ends are basic just like any other nitrogen would be, so it deprotonates the carboxylic acid, making a carboxylate. The protonated imine over here now is an electrophile. So the O- of the carboxylate adds to the protonated imide here, just like it would a protonated carbonyl, for instance. Okay? So it comes up, we have a neutral intermediate. Now we've activated it somewhat towards nucleophilic addition, right, by way of some electron withdrawing groups here, pulling electron density out, making that a little better of a C+. So regular plain old amine, any kind of amine, in the case of our protein synthesis above, it was another amino acid, but really any amine, so any RNH2, can now add to the carbonyl. Okay, here's our tetrahedral intermediate, which then collapses, right? The O- comes down, kicks out what now is an excellent leaving group. So the carbodiimide, right, is just a way of directly adding to the carboxylate as an excellent leaving group under neutral conditions, pretty much. It's kind of interesting what happens here, right? We form a CO double bond in DCC right here, which then forces this triple bond to go and attack a proton. So it protonates it. We get a nice neutral leaving group that's come off here. and that's how we get our amide. So C double bond O NHR. This is a little more complicated mechanism that I will not hold you responsible for this mechanism, but again, like the thionyl chloride mechanism, I may hold you responsible for identifying the function of certain parts of it, being able to see that this right here makes it a good leaving group, for instance, because protonation of that nitrogen gives us a neutral molecule that comes off of it, really. So DCC is always the coupling agent. Please do be familiar with this type of reaction. If I have a carboxylic acid and an amine, I can make an amide out of them. That's just a plain old synthetic transformation with DCC used as the reagent. Carboxylic acids can be reduced into alcohols. Lithium aluminum hydride is a strong enough hydride reagent, but just barely. If we look at what can happen here, it's really a very difficult reaction. The lithium aluminum hydride is a very, very reactive hydride source, right? And conditions really are pretty forcing. There's really no other functional group in the molecule that will be unaffected by this. So why do we need such forcing conditions? Well, any negative nucleophile like hydride here is also sufficiently basic. So the actual first thing that happens is this hydride deprotonates the carboxylic acid. So let's look at our mechanism down here. Here's our carboxylic acid. H minus deprotonates, right, making just H2 gas. So we have a carboxylate ion. It has an O minus. So that carbon is actually not very electrophilic. It's not very C+. So we have to have H-, which is a very powerful nucleophile, adding to there. And look at what we get as a result. We have two O-. It's a dianion. Okay? It's a very unstable dianion, and it's only possible because we also have aluminum in this mixture here. Aluminum complexes with those oxygens, meaning it forms partial bonds with them that stabilizes them somewhat. So if all we had was just two O-, there's no way that molecule would survive. Aluminum is able to do that. So this sort of intermediate here with aluminum complex to both of those O-, it's sort of like the four-membered intermediate in the Wittig reaction, right? We have the phosphorus and the oxygen and the two carbons making that four-membered ring. And the ring just sort of rearranges, right? The aluminum oxygen donates electron density in to make a carbonyl. Then we break the other CO bond to form a full aluminum oxygen bond. Okay? So it's only through this aluminum complexation that this step is even possible. So that's how we make our aldehyde, but it's an intermediate. Because remember then, the aldehyde reacts with another equivalent of H-, okay, to give us our CH2OH, right? Just by simple nucleophilic addition, right? H- as step 1, then acidic workup, right? To give the proton. And here, let me color code it here. It's the H on the OH that comes from the acidic workup, right? Take a look back at our aldehyde chapter if you're unfamiliar with that mechanism. Just a simple nucleophilic addition making an alkoxide, which just gets protonated in workup. It is really not possible to stop at that aldehyde with lithium aluminum hydride, right? As soon as we form that aldehyde, another hydride equivalent adds in, okay? So in general, we add two H's, eliminate one oxygen, essentially, right? The OH, or the carboxylic acid, is removed by the nucleophile in the very first step as an acid-base reaction. So one of the oxygens, I suppose, is removed by elimination with the aluminum. So we're left with just the carbonyl again and an H as an aldehyde intermediate. So hydride adds to that again, making the primary alcohol. As a common theme with our carboxylic acid derivatives in this chapter, lithium aluminum hydride will add twice to all of our derivatives in this chapter, making primary alcohols.